All right. I don't know why they do that part A, but it's okay. But they tell us to find the limit of h of x in question 1. And then they give us f of x to be 3x squared plus 2x plus 7. All right, and then they define on part A, h of x is equal to f of x over x. Okay, so let's set it up. So that'll be 3x squared plus 2x plus 7 over x, which technically reduces, right? You can divide each term by x, which will give us 3x squared over x plus 2x over x plus 7 over x. Okay, so that's going to reduce to 3x plus 2 plus 7 over x. So now let's take the limit. That's what they wanted. They just wanted me to create this h for some reason. I think they should have just given me this, but okay, that's cool. Limit of h as x approaches infinity would be equal to the limit of 3x plus 2 plus 7 over x. So treat each one separately. What is this limit going to do? As x gets infinitely large, what happens to this term? Do you remember? We'll think about it. As a fraction gets, as the denominator gets bigger and bigger, that means the fraction is getting smaller and smaller, right? So if it gets infinitely small, that means 0, right? That's what we typed a long time ago. This piece is going to go to 0. Okay. There is no x on this one, right? So no matter what x does, if this goes to infinity, it still stays as a 2. This has no impact on this. This guy, though, will become infinite, right? So infinite plus 2 plus 0, I mean, these don't even really matter anymore. It's going to be infinite, isn't it? Does that make sense? There's really nothing else to do. I mean, you could write this, I guess, but it's not a number. So these would be the 3 separate limits. So it would just be this. Any questions on part A? Not too bad, right? You guys okay? No rush. Did you finish charging or?
I'll charge it again.
Okay. Alrighty. On this one, they divide by x squared. So that means that we get 3x squared over x squared plus 2x over x squared plus 7 over x squared. So that will reduce to 3 plus 2 over x plus 7 over x squared. Right? So now just do the limit and see what happens. So limit as h goes to x goes to infinity for h. That will be 3 plus 2 over x plus 7 over x squared.
So 3 would be 3. Then 2 over x would be 0. 7 over x squared would be 0 also, right?
Yeah, it'd be a faster 0, I guess. Still 0 though, right? So it's just doesn't make a difference. So this is 0, this is 0, and you said this one was just 3. So we have 3 plus 0 plus 0. So 3. That makes sense? All right, we'll skip part C because it's the same thing. Let me give you some notes or some rule of thumbs, I guess. Rules of thumb? Yeah, that's better. Just a moment. Yes, cool on this page. Okay. Number 1. If the degree of the numerator is larger than the denominator, then the limit of f is infinite. So let's say my f function is some x to the n plus whatever over some x to the m. Okay. So if the top is bigger, the degree, you're going to get this. That's what I mean by degree, and that's the f I'm picturing. Okay. Number 2, if the denominator degree is bigger, right? So if the degree of the denominator is smaller, I'm sorry, larger, then the limit of f is 0. Number 3, if the degree or degrees of the denominator and numerator are the same, then the limit is is the coefficients trying to find an easy way to word this. I'm sorry. Is the quotient of the leading coefficients of the numerator and denominator. Okay. That is the most legit way to say that I can think of. Example 2, find each limit if it exists.
Can you read two again? Because
So if the degree of the denominator is larger, then the limit of f is 0. So larger than the top numerator. Maybe this will help. That better?
I don't know, we'll see.
It's like a quick little example of, like you did for number
No, this is for all of them. This is the f I'm talking about. Let's put an a and b here. So if, let's say n and m are the same, then the limit would be a divided by b. That's what the leading coefficient means. And we'll do an example for each one just in just a second. Promise. All right, so let's do one where I like this example. I'm going to change it up here. 2x to the 4th plus x cubed plus 7 over 3x to the 4th plus 2. Now, degree of the top is 4. That's the biggest one, right? Degree of the bottom is also 4. So if they're the same, the limit is equal to the leading coefficient divided by the other leading coefficient. Does that make sense?
Yes.
So basically, these overpower everything else, so we disregard everything else. And since they're growing at the same rate, they almost cancel each other out basically, and leaving you with these numbers. It's just 2 over 3. So that's the example of number 3 there. We don't care when we're dealing with infinity. Only the highest degrees matter. let's say x to the third plus 2x squared plus 3 over x to the fifth plus 7x plus 1. So what's the degree of the numerator?
Three,
And degree of the denominator?
5,
So the bottom one is bigger,
0.
limit would be 0. So the bottom is growing faster, so it ends up going to 0. That's what number 2 is saying. So I feel like it's a lot more intuitive when you have infinite limits.
And besides one of the hardest things to draw so far.
Okay, so here the degree on the top is bigger, right?
It would be infinite.
Bottom can't keep up, so it goes to infinity. Any questions on this concept?
And the test just be all that.
It'll be I think there might be 1 or 2. But not all of them. For test 3, you mean, right?
Yes.
Okay. Any questions on example 2? Yes, cool on this page. Let's do a couple more and then we'll move on because I feel like it's not too crazy. We got to do some hard stuff instead. So the limit as x approaches infinity of 1 plus 6 over x. What would be this limit? Yeah, it's going to be 1, right? And you can separate these. That's a property of limits and do them separate. So this goes to 0 and that's just a 1, right? So don't forget that you can use those rules. You can also pull numbers out in front of the limit if you need to. I guess we'll do one more because there is a few questions with negative infinity. It's almost the same. So it's just a slight difference. 6. Okay. So do them separately. It's like earlier. Okay. So this will still go to 0 because even though it's going in the negative direction, it's still getting super small. It's super negative and then goes to 0. Right. Over here, though, we said if the degree is bigger on top, it goes to infinity. But since it's negative infinity, it's going to go to negative infinity, but there's a minus. So it's actually infinity. Does that make sense? If there was a minus there, you would have said negative infinity because of the limit. Limit is going to negative. Right, like something like this here. Right? This guy would be negative infinity. Does that make sense?
So it's opposite. But even though that's a fraction, because the,
Yeah, I mean the 2 is just a number, right? Talking about this one?
the negative x over 7,
Oh yes. What about it?
well, it's actually both.
Yeah, you can pull out the 1/7 in front and ignore it. Because 7 is not going to do anything to infinity, right?
All of negative would be 0.
Like it would have to have a variable down there to affect anything. But it doesn't. Like, same thing as having this, right? That 2 is not going to do anything. So who cares if I have that's 7, right?
Oh, because the x is infinite.
Yeah, well, there's the only thing that's changing.
Okay, I get it.
You could also pull it in front and make it more obvious. You could say,
I finally got there.
that's all good. All right, let's move on to the more challenging section. Any questions on infinite limits? Does the concept make sense?
Yes.
Just look at the degrees and you'll be good. Okay. Pay attention if it's negative infinity. And a paper. It's a grid paper, I guess. Okay. So to save a little time, I'm not going to show all the derivatives, like the quotient rules and chain rules. I'm just going to give it to you and we're going to move on. Because it takes a lot of time and you should know how to do a quotient rule by now. And if you don't, we need to talk about your section chapter 3 stuff and I need to help you out. So chapter 4 assumes you are a pro at derivatives, or at least decent.
right here.
All right, so problem 1. It wants us to find intercepts, extrema, etc. And then it wants us to sketch it. That's basically where we're going with this, right? We're going to sketch the graph with all this information and then compare it to the actual graph on Desmos or something, or your calculator. Okay. So, forgot to show that on this thing, dang it. We're doing this question. We will find these first, and we need the derivative. Sketch y equal to x over x squared plus 4. Find all extrema, points of inflection, intercepts, and asymptotes. So the derivative is going to be this. So I'm skipping this step here. You will need to do a quotient rule to find this. Okay. Now set that to 0 and find the critical numbers. That's what we're going to need. We will probably need the second derivative, maybe. Let's see here. No. Anyway, so set this to 0 to find the extremos, right? Criticals. The denominator is not going to have any effect on this problem. Since it was since we had well, actually, no, we're not going to have any zeros down here, so we're fine. We only care what makes it 0 on the top, though. I believe this was negative. I'm sorry, there was a mistake there. The negative should be on the x squared, not on the front. But yeah, it looks like it's going to be 2 plus or minus 2. So just set the top to 0. Solve for that. So x equals plus or minus 2. And you square root both sides. That's what you're going to get. You divide the negative out, get to here. So these are the critical numbers. Okay. Do you see why the bottom cannot be 0? Right, no matter what x I choose, it's going to be squared. So it can't come out negative. It cannot subtract 4. So there's no asymptotes to worry about, at least not vertical. There might be a horizontal. No, I don't think so. Anyway. But yeah, the asymptotes usually depends on what makes the bottom 0. But in this example, we don't have to worry about it. Okay, so let's test around these values. So we got critical at 2 and -2. So let's test 0. If I plug in 0 into the derivative, looks like I'm going to get positive. Go ahead and show our work. The derivative at 0 would be equal to -0 squared plus 4 over 0 squared plus 4 squared, which is 4 over 16 plus. Derivative at 3 will be -3 squared plus 4 over 3 squared plus 4 squared. Is that negative or positive? -3 squared is 9. -9 plus 4. This is going to be some number I don't care about, but it's going to be negative. Do you see that? Do you see that the denominator doesn't matter? Because no matter what I plug in, eventually I square the whole thing. So the bottom is going to be positive no matter what. So let's not even bother with the bottom. So all we have to really look at in this particular example is the top. Now, derivative at -3. Make some more space there. I don't really give a crap about the bottom. So -3 is going to be 9 negative plus 5, again negative. If you're really curious, you can plug it into your machine and you're going to get plus, minus, minus. Okay. So that means we are decreasing until we get here. And then we're increasing, right? Make it a little closer, I guess. And then we're increasing and then decreasing again. So it looks like we have a minimum over here, maximum over here. Okay. So we have a relative max at 2 comma whatever that is. We'll find that in a second. Relative minimum at -2 comma something. So I need to plug this into the original function to get that value. You plug it in up here to the y. You're gonna get -1/4 and I think 1/4. That sound right? Yeah. Okay. So there's my maximums. Remember, all this information, we're just gathering information in order to sketch it. That's what we're doing. So I kind of have an idea where we're decreasing, have an idea where we have a minimum, have an idea where we're increasing, etc. So I don't need any inflection points for this one. Got maxes.
Well, it's 2 1/4, -2, -1/4.
Oh, they get the minus sign is opposite. Oh yeah, that makes sense. Thanks. Turn the page in a second, and then we got to find the intercepts. So we got this information. We got this to help us out. Now I need intercepts. So that's like college algebra stuff, right? Maybe, yeah, around there somewhere. Plug 2 into here. So 2 over 2 squared plus 4 gives you 2 over 8, which is a fourth. Just to save space, plug the 2 into to y, or to the x value, sorry. You guys cool on this page? Don't scratch it. Just cut your nails. We'll put this little baby mittens. You guys cool? Which one? This one? Yeah, so you got to do a quotient rule. So when you do it, you're going to get this at the end. So I didn't show it because it's ugly, and it's going to take like this much space. Did you want to see it? Okay. So in the question, you got to find the derivative of yourself. Here, I just gave it to you. Right, so continue, same question. I'll write the problem here so I don't forget what the heck we were doing. So let me give you some notes in case you forgot. So to find the x-intercept, let x equals 0 and solve for y. Hold on. That's the y-intercept.
Zero fourths.
Yeah, it's going to be 0, 0. Yeah, it's going to be 0. To find the x-intercept, the y equals 0, and solve for x. Okay, so x-intercept. Y is equal to 0 over 0 plus 4, which is 0. So 0, 0 is one of the intercepts. It's the x-intercept that I was trying to find, but it turns out to be going through the origin. Yeah, it looks in this case, x and y-intercept are the same. They go through the middle. So if you try to solve it, you're going to get the same thing. Mm-hmm. Yes. Yes. You're going to need to start drinking Monsters again.
Oh my God.
I I stopped for a long time. I'm like, man, Monday, Wednesdays are killing me. Okay. So if you try to solve, you're gonna get the same thing. So we're gonna skip that. Because the only way that this is equal to 0 is if x is 0. That's the only way. So that's why I said this is 0. Okay. Which means you got the same intercept. So using all this information, sketch it. So you're gonna have one question where I'm gonna make you sketch it. That's it, just one time, one example. Because you can see it can be very involved. You may require doing more things, depending on the question.
Or what's the punishment?
Yeah. Okay, so what was the maximum and minimum?
Max was 2 1/4.
Okay, so I'm gonna make this scale to be 0.5 and 1 out here. This would be 1 and 2. Okay, that makes sense. Same thing for this side. All right. So we had a x and y intercept at the origin, right? Where was the max at?
2 1/4.
So 2 and 1/4, so about here, right? So we got this thing going on here. Then we had a minimum at -2, somewhere, -4, right? So about here, we had a minimum. So the sketch is going to be something like this. And then it starts to decrease after that. Over here it begins to increase. Something like this. So using the first derivative test and the intercepts, I got a sketch. Okay. So several hundred years ago, this was awesome. Let's see what it looks like for real. See if I'm close at all. I don't know. Okay. I called it y in this case. X over x squared plus 4. Yeah, check it out. It's kind of close, right? Not too shabby.
So use again?
Mine's something.
Yeah, it both.
Almost there. It's almost the same. Almost. But you see the idea, right? We're using idea of max and min, increasing, decreasing. You can figure out what it looks like. Now, I'm not gonna test you too much on this because it is a little annoying. Okay, let's do another one, and I guess maybe we'll call it there. This time we're going to use the second derivative test, I think.
So how come this one didn't need the second derivative test?
We could have. So you can use either one. So the rule of thumb would be, do you want to take two derivatives? Is it easy to do? If it turns out it's a real pain, then maybe just stick to the first order test. I think the second one's a little better because you can just plug in the critical number and it'll tell you max or min, right? Because it tells you about concave up or down. Whereas first order test, you got to test around it, so it's more testing technically. So second is a little better, but if the derivative requires like chain rule quotient nonsense, do you want to do that again? Probably not. So you might just stick to the first derivative test. But if it's an easy function where the derivative is not that painful, then I would go for 2. That makes sense. It's like for example, this one, I didn't show it, but doing 1 was a real pain because it was a quotient. But when you do the quotient, it gets nastier. You have to do it again, so it'd be even uglier. So let me show you. You guys cool on this page? Any questions on the concept? This time we will do the second derivative test, but I am going to skip the derivative again because it's disturbing. And if I do both derivatives, we're going to stay here another 45 minutes.
Oh, I'm hungry.
So to save a little time, because this chapter is not about derivatives, it's about applying them. Let's just do it. So analyze and sketch. So in order to sketch, we need to find intercepts, relative extrema, points of inflection, on the other one I didn't do inflection because I didn't do second derivative. This time we will. And asymptotes, if they are there. So y is equal to x squared over x squared plus 12. So first derivative is going to be, did this earlier to save some time, it's 24x over x squared plus 12 squared. That's a pretty version. Second derivative, all polished up for you, is negative 72 times x squared minus 4 over x squared plus 12 cubed. Okay, that saved me 3 pages there. It's nice. Okay, that's everything we need. Now find critical numbers, find inflection points, find the intercepts, and that should be more than enough to fill in the blanks, right? Okay. So critical numbers. Set prime, y prime to 0, 24x over x squared plus 12 squared equal to 0. The denominator will have no will not affect and will not make the 0 ever. It's only the top. So you can see that the only thing that'll make the top 0 is the 0, right? It's the only critical number here. So x equal to 0 is the only critical. Does that make sense?
Say it again.
So if you look at this without doing any work, if I plug in a 0 in this x right there, you're gonna get 0 times 24, right? which is a 0, and then 0 over anything is a 0. That's the only way this is going to happen, right? There's the only way this will become a 0 is if this particular x is 0. There's no other way. If you try to solve for it and do the work, this bottom part does nothing because there's nothing I can divide by to make it a 0 unless we're doing limits or something.
So like a general rule for this, the denominator will never actually count for anything.
The denominator is never going to make anything 0. Only thing in the denominator would matter would be when we're testing stuff, like for increasing, decreasing, or if it cancels something on the top. That's when it would matter. But other than that, when you have a fraction like this, you only set the numerator to 0. Technically, what you should do is this, right? And then you solve. But anyway, I think that's not necessary, right? That makes sense. Okay, so now let's do the inflection point. So negative 72 x squared minus 4 over x squared plus 12 cubed. Oh, I did mention, well, this is a while ago, but at the beginning of chapter 4, I did say if you take a derivative and suddenly there's a new value that's undefined, but it used to be defined in the original, then that's a critical. So that could be where the denominator matters. Like you had a function like here, 0 is cool, right? There's no problem plugging in 0. So you do the derivative, you're gonna get 1 over 2 root x, right? Now 0 is not cool. So 0 would become a critical number because it's defined here but not there. So remember, I wrote that note a long time ago, beginning of chapter 4. So if something made this thing 0 at the bottom, but not here, not in the original, then it would be critical. But there's nothing that's going to make these 0, so it doesn't matter here. Does that make sense? Okay, so keep an eye out for something like this. What's up?
They're not right now, but maybe it will.
Yeah, so if in this case it's not going to matter, but if there's an example that creates a situation like that, then it does matter. Okay. So an undefined point in the derivative could be a critical number if it is defined in the original function. Okay. If it's undefined in both, then who cares? Just ignore it. Okay. Like if you had something like this, right? A negative 3 is undefined, but then you had this again as a derivative. Still doesn't matter. Okay. Yeah, that was just reminding you because that was a while ago. Okay, so inflection point. We only care about the numerator. So set that to 0. The negative 72 x squared minus 4 equals 0. But 72 doesn't matter because you can divide it out. X squared equals 4. Square root both sides and you get x equal to plus or minus 2. So do your algebra and you're going to get this. Okay. Okay, so we have 2 inflection points. Weird. All right. number this. Too much going on here. So now let's test the critical number in y double prime. So we're going to use the second derivative test here. So negative 72 times 0 squared minus 4 over 0 squared plus 12 cubed. Is this going to be negative or positive? That's going to be negative 72 times negative 4, right? Over 12 cubed. It's going to be positive, isn't it? This tells us concave up. Therefore, minimum. So we have a minimum. Well, let's call it relative minimum. At 0, 0. Do you see why it's 0, 0? Right. If you plug in 0 here, what do you get? Yeah, so location is 0, 0. All right. So now we have a minimum of inflection points. Now we need intercepts. That should be enough to graph this nonsense. Although I think we also have an asymptote, right? Do you notice the degrees are the same? So we can use those ideas of infinite limits here. If you were to take an infinite limit, it would be equal to 1. So that means you have an asymptote at y equals 1. So that's something from college algebra. That's when you would have oblique asymptotes. But anyway, let's go ahead and do the intercepts. That's cool on that page. I know. And this is me trying to shorten it up. I've cut out like quite a bit of stuff and it's still super long. Oh, anyway, intercepts. What number are we on? Step 4 or something? 5. Find x-intercept.
It's on the same question.
Yes.
Really?
Yeah. Same question. I'm gonna write it down again because I forgot what it was. We're trying to get information to sketch it. That's what we're trying to do. We don't have enough yet. Almost do. So it looks like, oh, it looks like the same type of deal. X-intercept at 0, 0, y-intercept. So it's going to be the same thing through the origin, like the last one. So if you try to solve it, letting x be 0 makes this 0, let y be 0. Same deal. Oh, well, who cares? All right. So let's try to sketch it now. we had X and Y intercept at 0, 0. We had a minimum, right? At 0, 0 as well. Well, that's not enough information. We had inflection points, right? Inflection. Inflection at 2 comma something. And -2 something. We have a minimum. So we got this going on down here. So that's cool. If you plug in 2 in here, what are you going to get? 4 over 16, right? 4 over 16 reduces to a fourth and a fourth. Okay. Make you a note here. Plug in 2 and -2 to find the y values. Okay, so that's a little bit more information. So 2, 1/4 is about right there. -2 and 1/4 is about here. Now,
You plug those into the second derivative, right? Or the first derivative.
this one? No, I plugged them into, well, I use the second derivative to find the x values, and then I plug them to the original to find the location. So we are increasing on the way there. And since this is a point of inflection, it should start decreasing, right? Increasing and then whatever. Something like that. That's what I'm thinking. That is my sketch. Yeah, because you're going to square the negative. So it's the same thing. Me too. Okay, let's see what this awesome drawing looks like. Hopefully it's not complete garbage. Maybe it is.
Since it has a relative minimum, it doesn't have a match, right?
Yeah, I mean, in this case, there's only a minimum, but there could be both. So it looks like,
Child's drawing of the
yeah. Yeah, look at the do you see the asymptote? It's approaching 1. So there's an asymptote up here. And that's because of the degrees. So up here, so the function is technically approaching the asymptote. That's more accurate. Once you put the asymptote in, it makes more sense. Now, when you're trying to find horizontal asymptotes, you think back to the infinite limits. If the degree is bigger on the bottom, right? The degree on the bottom is bigger. Your asymptote will be 0. Y equals 0. The degree on the top is bigger. You're probably not going to have an asymptote. But you'll have an oblique asymptote. If they're the same, though, you take the coefficient, right, which is 1/1 in this case. That's why we had a 1. So just think back to what we just did in the last section, okay? If it's bigger on the bottom, we're gonna asymptote at 0. If they're the same, find out what that number is, A over B. If it's the top is bigger, you're gonna have to do long division, which sucks. Anyway, you'll see that you might see that in 4.5 maybe. I don't remember. Any question on 4.6 though? Do you see the main idea? Where you're just gathering information, plotting it on the paper, and you're trying to do your best guess, right? It's just a sketch. So on your exam, I'm not going to be like measuring stuff here, right? It's just a sketch. But I will expect you to have the minimums, intercepts down, written somewhere, inflection points, all that stuff should be written down somewhere. That's going to be majority of the points, and at the end, you just do your best sketch.
Can I see the page before this real quick?
Yeah. You're only going to have one of those types, but
Down to 3.
the entire chapter 4 is about finding critical numbers, finding max and mins. So that's the majority of this question anyway. Yeah, probably.
Oh, I got it.
All right, guys. That's all for today. You guys have any homework questions or anything?
So this weekend. So I don't confuse myself.
Okay. Yeah, if you guys want to head out, you can. If you want to stick around, you can too. It's all good. So next week we'll hit 4.7, 4.8, and then review for test 3.
How many questions is test 2?
I don't know. Let me see. Should say on there, right? I don't remember if I wrote it.
I don't really want to click on it. Oh, there's extra credit.
Let's see. I have to.
Or we just all sneak it together right now.
To open it up. Hold on a second. 13. What's up? Yeah, test 2.
So one of them is doing derivatives without any. I think that takes me 2 hours in itself.
Which one?
Doing derivatives